Hi, thank you for joining another lecture for interactive computer graphics. Now, this is the second half of this course, so we will be talking about topics at a relatively high level. That's the idea. So we're not going to go into that much detail in general, but today I am actually planning to go into a little bit of detail. Not a lot. Because these are not going to be stuff that I'm expecting you to go and implement right away, but I'm still going to give a bit more detail than I'm planning to do for the other topics, because today's topics are going to be some interesting, relatively newer shader models that we have. More specifically, we're going to talk about compute shaders, and we're going to talk about mesh shaders. That's going to be our topic for today. Okay. All right, let's jump into today's topic, starting with compute shaders. Yeah. So this stuff, you may think that, oh, compute shaders, that kind of makes sense, right? If I have a GPU with lots of parallelism, then I should have something other than graphics that you should be able to do, you would think. But no, the GPUs were designed to do graphics. So this is our GPU graphics pipeline. We've seen this. This is the relatively simpler version of it, right? We just have this vertex shader up here. So this is the GPU graphics pipeline. But as soon as we had that, as soon as GPUs allowed these completely programmable shaders here, people started using this for stuff other than graphics. So output here is an image. That's what it's designed to do. But I can interpret this image however I like. So these RGBA colors that I'm outputting from my fragment shader, they could have different meanings than just color values, right? I could use them to encode some other information. It doesn't really matter what that information is. It really depends on what I'm trying to do on the GPU. But if I use this output as some custom data, it's RGBA, it's just 4 bytes, right? And I can interpret those 4 bytes however I like. And I have a lot of these pixels, so a lot of output coming out of the fragment shader. So I can actually use this graphics pipeline to do massively parallel general purpose computation. And all I need to do is to interpret this data differently. So instead, yes, the output is going to be an image, but I'm going to interpret it as some kind of like my data, whatever that is. And by doing this simple thing, I retargeted my GPU rendering pipeline for general purpose computation. So that brings out GPU, that's the general purpose computation on the GPU. That's it, really. So the thing is, though, I'm not actually drawing vertices here, right? Because I'm not actually trying to render anything. This is just some custom data that I'm producing. So it's not going to be some vertex data, but some custom data, my input data, whatever that is. Actually, it's not the only place where I'm going to get some data. I also have access to other types of data in my shaders, right? So what kind of data do I have access to? I have access to uniform variables. Oh, okay, they're just parameters. But I also have access to all sorts of textures, right? So I can send data as textures to my fragment shader and use them. And this is custom data. I pack my data, whatever that is, as a texture, and as long as it's packed as a texture, I can access it in my fragment shader and use it. It doesn't have to represent any meaningful texture image or anything. It doesn't have to correspond to anything that we perceive as texture. It's just some data, I pack in some texture storage, and I can just put multiple texture data like this and send it to my fragment shader. Well, with this model, actually, I don't really need a rasterizer, do I? Because I'm not really rendering any triangles. So I'm not actually doing any graphics in here. So I don't really do, I'm not doing rasterization-based rendering. I don't need this at all. If I don't need this, I can just sort of simplify this stuff quite a bit and just do all of my computation in my fragment shader. And that's what people did. So they would typically render at like a screen size quad. So this data would be just a screen size quad, and just flap it on, just put it on the screen. And then this rasterizer would just basically generate one fragment for each pixel on the screen. And there you go. That's what I have. I have a fragment for each pixel on the screen, and I can just use it. So people did that a lot. I've done this a lot. It's nice, it works, but it's a little bit annoying because the end result, the end goal might be graphics, but the thing is, I'm not trying to do any rendering here, right? But I am still using the rendering pipeline. So all the stuff here, like rendering this quad, this vertex shader, this rasterizer, they're completely useless. They're just wasting energy. They shouldn't be there. It would be much nicer if I could just send my data to my fragment shader. Actually, I'm not even sending anything to my fragment shader, right? This is just creating a fragment for each pixel, and that's it. All I need to know is that fragment ID or pixel ID. That's it. I don't need any data that's flowing through this graphics pipeline. I'm not using anything, right? So I can just get rid of all of this part and make things a lot simpler, a lot more efficient. And so we had that, actually. We got rid of all of the graphics pipeline stuff that was completely unnecessary for general purpose computation on the GPU. And we started here, sort of. And we by getting rid of all this stuff, we ended up with a compute shader here. That's a way of thinking about compute shader. Compute shader is not a fragment shader. Fragment shaders are very specific. They have very specific job, they have very specific input, very specific output. Compute shaders are different, but it's a good way of thinking about how they evolved. So in a compute shader, as I said, it's a little bit different. So yeah, I'm going to have some texture input and some output. And that input doesn't have to be texture. In my compute shader, I can access all sorts of buffers that I have, with like the buffers that we've been allocating. We can access those in the compute shader. In addition to that, it's a shader, so it has uniform variables, so we can access those uniform variables. So all this stuff is accessible in my compute shader. But its output is a little bit different. So a fragment shader would output one color, right? That's the output. For a compute shader, I'm not actually trying to output any color. So this output data does not have to have any color format. Right? So because of that, we have some custom output formats that we can use, output types that we can use for compute shaders. So what's introduced with the compute shaders was this concept of shader storage buffer. So it's a different type of buffer that allows us to output into it from a shader, not just read from it, but I can also read from it. I can write and I can read into and from a shader storage buffer. In addition, if you like images, if you like textures, and you want to use image-like things, this sort of unstructured data, like just this could be like an array of something. But if you want to have some concept like 2D or 3D image, like volume data, things like that, it might make sense to think about this data as like an image. In that case, we have a more helpful alternative to shader storage buffer. That's the images. So we can write to images, we can read from images. Images and shader storage buffers are stuff that we can use for compute shader output. We can also use them as inputs. So it's probably better to think about them like this. So they're in a compute shader, I have access to different kind of things. Some of the things are the old things that already existed before compute shaders, like textures and buffers and uniform variables. They are read-only. They have been read-only for all of our other shaders, so we still have access to those. In addition to them, now we have two different types of data. They're sort of unstructured. I can specify what exactly they are, however I like. They're images. Images are supposed to be images, so there are some structure to them. The shader storage buffer is more flexible. I can specify it however I like. And these two are read and write. So in a compute shader, I can do whatever I want, and my output is going to be put into one of these or nothing. If I decide that a particular execution of a compute shader is not supposed to output anything, I don't have to output anything. So that I have that flexibility as well. So that's the idea, really. And basically, this came out of a little bit of necessity. Like, people have been using GPUs for general purpose computation. And because GPUs were not designed to do general purpose computation before we had compute shaders, that stuff was a little unnecessarily inefficient. Right? And by adding these features, these relatively simple features and compute shaders, that sort of opened up this whole possibility of using GPUs for general purpose computation. Right. So let me talk about these two new types of data storage, data access we have in the compute shader. Just a little bit. From this is GLSL. In GLSL, I can have images, and images are like, could be image 2D or 3D, 1D. But I have three types of image data. It could be floating point data, it could be integer data, or unsigned integer data. So typically, if you look at OpenGL documentation, you're going to see this G prefix, G image. That means it could be nothing. That means it's float. If it's I, it means integer. If it's U, it means unsigned integer. That's what it means. So it's basically a way of representing all of them. This is how you can get data from images or write data. So if you want to get data, if you want to read image data, you can use this function. Image load. This is my image resource, and this is my image coordinate. So it's very much like reading a texture. There's a little bit of a difference though. This is not doing any texture filtering. So filtering was a very, very important thing for textures, right? We talked about this quite extensively. But for accessing images, I don't want to do any filtering. So I'm basically using this image storage as some data, some custom data that I have, and I want to be able to access that data directly. Like, I don't want that data to go through any filtering operations, right? I want to access it directly. Well, if I want some filtering operations, I could use a texture maybe. But so if I'm using images, that means that I don't want any filtering. So there's not going to be any filtering component. So this image coordinate is going to be an integer pixel coordinate. So I just basically say, I want this pixel, and I get that pixel, right? That's the idea. You just read a particular pixel. If it's a 2D image, you provide a 2D coordinate. If it's a 3D image, you provide a 3D coordinate. If it's a 1D image, you just provide just one integer index, and that would be your pixel, right? That's the idea. Very simple. So this is how I load data from an image. If I want to write into an image, I can do that. There's the image store function. I can call it from GLSL. There's my image, again, the image coordinate, and this is the data that I would like to write. There it is. All right. Very simple, right? So I can access those images. I can read and write from them fairly easily. Also, now, this is going to be a parallel computation machine, right? Massively parallel stuff. Well, oftentimes, we need to do some synchronization between threads, because there's going to be this massively parallel computation going on, and we may need to have some synchronization. And for that, atomic operations are pretty helpful. So we have some atomic operations we can perform on these images. So this is just some atomic functions. I believe these are all of them. But anyhow, my intention was not to list all of them, but here they are. Atomic add, min, max, XOR, atomic exchange. So all of these stuff that you can do to images, you can just basically change certain pixels of those images. Now, how do I get those images though? How do I define an image? We know what textures are, so how do they correspond to images? Here's how. So from the GLSL perspective, these are going to be my image types all of these. And OpenGL will see them as kind of like these texture types. So like a 1D texture would correspond to a 1D image, a 2D texture would correspond to a 2D image, and so forth. A cube map would correspond to a cube image. Yeah, we have cube image type. Actually, there's a bit more than that. So you can access, for example, for a 3D image, you can access slices of a 3D image as an array of 2D images. Right? So, and you can access, let's say, rows, I believe, of a 2D image as an array of 1D images. So you can actually access sort of higher dimensional concepts using lower dimensional image types as well. So you can access a cube map as 6 different 2D images. Right. So anyhow, so this is how they relate to each other, but we kind of need to figure out a way to bind some image data to an image, right? So I'm going to generate some image data and send it to my shader. The way that we're going to do this is that we're going to use the same things that we've been doing for textures. So like however we were sending data to our textures, we're going to use the same mechanism for sending data as images to our compute shaders, right? So for that, what I'm going to do is I'm going to have to create a texture and then put my data into that texture. But then in OpenGL, I say I'm going to bind that image texture. So basically you bind that texture to a particular image unit. This is the texture ID, that my texture, whatever that is. And this is the image unit. So image unit will be able to access the image of that texture. Right? That's how it works. So you can bind different mipmap levels to different image units because they're different images, right? So you can access them differently. And another important thing here is this access type. It could be read-only, write-only, or read-write, right? So obviously these are for optimization purposes. If you're just going to read from it, you should probably say it read-only. If you're just going to write without reading, you should probably mark it as write-only so that it can be optimized at runtime. So this is all the image stuff. So as you can see, this is basically texture storage packaged in a slightly simpler form. So there's no sampler, there's no sampling, there's no MIP mapping. So all this filtering related stuff is gone. We're directly accessing pixels. Believe me when I tell you, before we had images, accessing pixels could be a little bit of a challenge, could be a little bit annoying. So I know which pixel I want to access, and now I need to provide the correct coordinate and make sure that I'm using nearest filtering. So all of this stuff is sort of simplified quite a bit using images. And also we have write capability, which is very, very important. And read-write. You read and write at the same time. That's something we actually didn't have before compute shaders. So you could read from a texture and your output was an image, but you couldn't write to the same texture that you were reading from, because then the results could be unpredictable. I'm not even sure if that would work, but even if that worked, so all these atomic operations we did not have, and read-write was a problem. So with images, fix that. But still, storage type looks like an image, right? And sometimes we don't care. That's not what I want to generate. I want to generate some data that does not necessarily look like an image to me. So I don't have to think about how I could package it into an image. I can actually use more general structures. So for that, we have the shader storage buffer objects that I mentioned a little bit ago. So these are more flexible objects, whatever they are, it's not important. So in this case, I'm saying that I'm going to send a simple array of data. It's some integer data. It doesn't have to be integer array. It could be literally anything. So I take this, and what I do down here is very, very similar to how we've been sending data to our other buffers. Right? So we create a buffer, right? We generate buffer. We bind that buffer, and then we set its data. There you go. That's it. I sent my data to this buffer. Basically, just copied the contents of this array into that buffer. That's really it. The only thing here is that I bind it to a particular buffer, and I'm done. Now I have access to it in my compute shader. So these are more flexible data. Whatever it is, I just dump my data into that buffer, and then I'll have access to it in GLSL. I specify my structure, whatever it is. I say, hey, this was my buffer with binding 3. This is my structure, and it has an array in it of some size. I don't even specify the size here, right? Whatever the size of the buffer is, that's where it is. I don't have to. There are different ways of attaching it, and then you can access this data fairly easily, right? So this was my data, whatever something array, and I access this element, and I can write into it very easily, or I can read from it. I can also do atomic operations here too. I can have I can pick the location and say that, there it is, there's the data. I can do all sorts of atomic operations that are also supported with shader buffer objects as well. So these are very, very flexible, very, very nice general purpose data structures that I can use, and I can configure them however I like, really. That's the nice thing about the compute shaders. For compiling a compute shader, that's actually fairly easy. So when I'm compiling a compute shader, I probably don't need a vertex shader or a fragment shader or anything else. It's just going to be a compute shader, right? So I compile my shader. This is my shader source code. I compile it, and of course I should check for errors here. And if it compiled successfully, I can just attach that one shader into a new program and link the program. Link? What link? It's just one shader. Yeah, so it's just going to be basically a program that contains only a single shader. That kind of makes sense, right? So I think that this part is relatively trivial. It's even simpler than any other shader. Over here, I just have a GL compute shader type. That's it. Now, running a compute shader is going to be a little bit different, because I'm not going to be using any of my draw calls anymore. I'm going to be using this dispatch call. So it's going to say dispatch, GL dispatch compute is going to start running a compute shader. Now, how many instances of that compute shader should I run? I have this one shader that I wrote, but how many instances? So for that, we're going to have a relatively complicated structure. So get ready for it. We have groups. Now, groups of threads. So how many groups do you want to run? In each group, you're going to have a certain number of threads. We'll get there. And I want to have a certain number of groups. So groups will have their own local storage, and they will be able to access their own data more efficiently. So I want to have this concept of a group. You can think about a group as like a collection of threads running on the same warp. A warp is a collection of cores placed together, right? They have access to the same local resources. So I'm going to run everything in groups, and I need to specify the number of groups, number of work groups. And for that, I am allowed to think about my problem, whatever problem I'm trying to solve, as a 1D problem or 2D problem or a 3D problem. So I can assign these work groups, not just say I want to have 10 work groups, but I can specify them as I want to have certain number in X, certain number in Y, certain number of Z. So it's really like, let's say I want to have a certain number of work groups in X dimension, like in this case I have 6, and I can say I also want to have some dimension in Y. So now I have 24, right? And I can have some dimension in Z. So this could be my entire computation work group distribution. Now this you don't have to have them in 3D like this. If it makes sense to you to have them in 3D in your computation load and whatever it is that you're doing, you can do that. That's very easy for GPUs to do, so it is supported. But you can also say, oh, I want to have just 1D. In X, I want to have 100 work groups. I'm done. I don't need the X, Y and Z will be just one, right? That's fairly easy. That's definitely doable. If this 3D structure does not make any sense for your custom computation, you don't have to have it. If you want 2D, you can have 2D. If you want 1D, you can have 1D, but you have up to 3D here. So when you say DL dispatch compute with this number of work groups in X, Y, and Z, you're going to have a structure like this, right? Now, each one of these work groups, each one of them is going to have a number of threads in it. And again, these number of threads are going to be specified in 3D. Because why not? We can do that. So work group size in 3D is going to be X, Y, and Z. So this is going to determine how many threads I have inside a work group. Okay? So in this example, I have, 3 by 4 by 2. So 24 threads. That's probably not great. I'll tell you in a second why. So, but you specify that the work group size in GLSL. In this case, these were the numbers. So your GLSL code for your compute shader will specify your work group size. So that shader will be written for that particular work group size, right? And when I'm dispatching this compute shader, I can dispatch any number of copies of this work group in X, Y, and Z, right? So it's a larger group and a smaller number of threads in here. Now I said this is not great, 24, because oftentimes we're not going to have 24 threads in a warp on the GPU. So GPU cores are structured such that a certain number of cores are placed in a group that NVIDIA calls them warps. So these warps sort of operate in SIMD groups together. So it kind of makes sense that if I have, let's say, 32 threads in a warp, probably my work group size should be 32. Like when I multiply these three, I should get 32. Otherwise, I'm not fully utilizing all of my available cores on the GPU. So if I just give this group to a warp, not all threads will be doing stuff, right? Because I'm only using 24 of them. So it kind of, that's why I'm saying 24 is not a good number. So you kind of need to know what your GPU supports. It might be different for some GPUs. Anyhow, so this is going to be the structure. I have this local structure of a work group, and I also have a bunch of groups when I dispatch a compute shader. So inside each execution, I will need to know where my thread is. So for any of these threads that's running a compute shader instance, it needs to know where it is in this whole work group, and within its own work group where it is, right? It needs to know all this local and global information. And we will have access to all that. These are predefined variables that are available in compute shaders. So you can have the number of work groups in X, Y, and Z. That's the data you send to dispatch compute. The work group size, same as whatever you specified in your shader, or work group ID in X, Y, and Z, and local invocation ID, that's going to be your local thread ID, or global invocation ID, it's in the whole global work groups and local threads. You can have a global invocation ID. Again, that's X, Y, and Z. And also there's a local index that's just a 1D version of your local invocation ID. So all of these IDs you can use to specify where that particular execution is in your workload. So you can decide, you can use that to decide what part of your data you want to access in that execution and what you want to output. So there is no limit here in the sense that a compute shader can access any part of your data and output into any part of your data. But if you make things a little more organized, such that a particular execution of your compute shader in some place in this 3D workload accesses a location of the data that matches that location, then you're going to have some similarity in neighboring threads accessing similar things. So you're going to have you're going to get a lot more performance out of your compute shader that way. So it kind of makes sense to keep things organized as possible, but there's no limit really. In your compute shader, you have access to your entire data. In every execution of your compute shader has access to all of your data. All right. So let me give you an example compute shader that does absolutely nothing useful, but it's a full compute shader that works. This is my buffer. I'm sending my buffer. It's just going to be a unsigned integer of 3D unsigned integer vectors, and I'm specifying these funny numbers here, right? 8, 4, 16. So this is kind of larger than what a warp would support, but you know, this still compiles fine. I'm not saying that these are good numbers, but these are still some numbers that are supported. So you kind of need to figure out what a good number is for your particular GPU. But anyhow, what this compute shader is doing is that it's just outputting its global invocation ID to a corresponding position. Just fill an array with some numbers, with some integer numbers. That's what it's doing. Not a great compute shader use case, but yeah, it's a very simple example of a compute shader. So as you can see, it's really nothing scary here. Like, it's just another GLSL shader, and you have access to all of your data fairly easily. Writing a compute shader is, in some ways, much easier than writing any other type of shader, because you have complete freedom in sort of how you access your data and how you structure your data. It's in many ways, compute shaders are fairly easier to use than other shaders that expect certain specific things and accept certain specific types of inputs, and only you're required to provide certain types of outputs. In this case, you have a lot more flexibility, is what I'm trying to say. One more thing. When you're running a compute shader, obviously, you kind of need to, you need to say, I'm using this program. It kind of makes sense, right? You need to bind it, and then you say, I'm dispatching. And now you might be outputting some data that will be used later on for rendering purposes. That data could be maybe modifying some texture data. This is different than render to texture. You're actually doing a different type of computation to produce that texture data. Or you might be generating some buffered data. Like, for example, you might be moving some vertices around. You might be simulating a particle system. You do fluid simulation. You have lots of particles. You figure out where each particle would go, and then you're going to use those particles for rendering, maybe, right? So if this output is going to be used for something else later on, you want to make sure that what happens later on will wait for this to finish. Now, this is not necessarily guaranteed if you don't enforce it. So your the dispatch compute might be running on some of your GPU cores, and if there are still available cores, they could be used for other things. But if those other things, those next operations, would require this stuff to be complete you can actually say that. You can say, oh, I'm going to have a memory barrier here. You say, I have a shader storage barrier here, so you kind of need to wait for that to finish before you start using that buffer for doing other things, right? So you put that, and all of your operations that come later on will wait for your compute operation to be done. Right. So this is the general idea of compute shader. It's actually fairly simple, and in many ways fits the way that GPU operates much better than our other shaders. So let me show you a few relatively old examples of compute shaders. This is from 2009. In this case, compute shaders are used for wave simulation, open ocean wave simulation, using fast Fourier transform. I believe this is a version of, probably it's a version of Jerry Tassendorf's wave simulation technique, but it doesn't matter. So basically it's doing some compute on the GPU to figure out where these vertices of this open ocean is supposed to be. I believe, I haven't checked this code, but probably it's possibly outputting an image rather than positions of vertices. But anyhow, it's a ocean simulation, ocean wave simulation you can do with a compute shader. And then, yeah, the goal is, in the end, is to have some graphics output, but you're computing these textures on the fly using general purpose compute operations, right? Here's another example. Again, is ended up being a fluid simulation example. The video looks a little odd because I believe this is captured by a camera on a display, so that's why it looks a little shaky. But you know, it's SPH-based fluid simulation. I believe this is SPH, the smooth particle hydrodynamics, computed using compute shaders, and then you render it however you like, right? So just some examples of compute shaders. I mean, it's general purpose compute, so you can use it for all sorts of things. Now, compute shaders are not the only way of using your GPU for general purpose compute. So we have OpenCL that you can use for doing general purpose compute on the GPU. We have NVIDIA's CUDA that you can use for, again, general purpose compute. So compute shaders are just an alternative to those. The nice thing about compute shaders is that you use GLSL code. With OpenCL, you kind of need to use a different sort of programming model. With CUDA, you kind of need to use CUDA programming model. They're a little bit different. Another nice thing about compute shaders is that it runs inside the same OpenGL context that you have. So if you're going to use the output of your compute shaders for graphics purposes later on, for rendering with OpenGL, it makes things quite a bit more convenient because it's using the same OpenGL context. It has access to all of your OpenGL context data, so you can easily send your data to and from compute shaders, right? So that's the idea. All right, so let me move on to the newest shader that we have. It is mesh shaders. Yeah, mesh shaders are the newest stuff that we have that changes the graphics pipeline quite a bit, actually. So, and I want to talk about compute shaders first. This is graphics. Compute shaders was just general purpose compute. I want to talk about compute shaders first because these are sort of closely related to compute shaders, actually. All right, so what's going on here? Now, you remember our GPU graphics pipeline. So we've been using this for rendering. And it's great, it works well for what it does, but it has a few problems, actually. When you look at this, I mean, as a programming model, it's great. I'm getting per vertex data here, which is good. And then over here, I'm getting primitives. Yeah, but right, this was per vertex and then per primitive. And then I switched to per vertex here again, right? In the geometry shader, I get per primitive. So I have different levels of parallelism here, right? So there's per vertex parallelism, and then this is also running per vertex. You'll remember that we talked about tessellation control shaders running per vertex. So it has the same parallelism here, but over here I have this explosion of data. All of a sudden I have a lot more data because I have this tessellation in between, and this is running per vertex, and then I switch to per primitive in the geometry shader. And then the output of the geometry shader, who knows, could be whatever. So optimizing this becomes a little clumsy, I guess. And the funny thing is that this sort of fits our rendering model, rasterization-based rendering model, and this is designed for rasterization-based rendering, right? So it's the rasterization-based rendering pipeline. But this actually does not fit the way that GPUs actually run so well. So I mean, if you look at the actual hardware that runs this pipeline, yeah, all this stuff doesn't really fit so well. I mean, I have certain number of cores in the warp, but this is like per vertex here, per primitive over there. This whole scheduling everything and doing this efficiently becomes a little hard. So it's not a direct mapping between how the hardware operates. There's no direct mapping between how the hardware operates and how this pipeline works. Like, this pipeline is its own thing, and the hardware that actually runs this pipeline looks quite a bit different. But we have one shader, one special shader that looks very much like how the hardware operates, and that's going to be, big surprise, compute shader. That's really not connected to anything. Doesn't have a specific input, doesn't have a specific output. It's its own thing. It just, I mean, yeah, this is designed to do general purpose compute on this hardware we ended up having. So yeah, this actually maps this hardware pretty well. This concept of work groups actually is great, because that's how GPUs are designed today. And this allows you to do things that you couldn't quite do with all these other shaders. Like in the compute shader, I know what my work group is, so I can have some local storage, and I can pass data between different threads in a local storage. But good luck trying to pass data between neighboring vertices in a vertex shader. I mean, you can't do anything like that, right? Even though maybe it's right there, it's operating right next to you in the neighboring thread, and hardware provides that capability, but your vertex shader does not expose any of those hardware details. So, I mean, this graphics pipeline works fine for rasterization purposes, but it's not a great match to the actual hardware that runs it. So because of that, maybe we're missing out on things, right? Maybe this is a little too complicated in some ways, or maybe there are things that we could do if we could only have access to the hardware as if we're using some general purpose compute. The whole concept of mesh shaders actually is designed to simplify all this mess and make it look quite a bit more like how the hardware operates. So all this stuff that comes right before rasterization, this vertex pipeline, vertex primitive pipeline, all this stuff will collapse into this one mesh shader. There it is. So when you have mesh shader, this whole pipeline simplifies quite a bit. I just have my data, mesh shader, rasterizer, fragment shader. So like, this is, you can kind of think about this as like an Uber vertex shader, but it's not a vertex shader, right? It's not operating on per vertex or anything. It is actually, if anything, this is more like a compute shader. This is a very specific type of compute shader. It's a compute shader that outputs primitives. I think that's the best way of thinking about the mesh shader. It's a compute shader that's going to output primitives. Now, very much like a compute shader, its input is going to be sort of unspecified, right? I'm not going to pass through some vertices into this mesh shader. No, it's going to get custom data, just like a compute shader. It will have access to all these textures and images and buffers and whatever. All of the stuff it will have access to. And it will output some primitives, right? So I'm going to get rid of this stuff that comes after rasterization, because that part is the same, right? The only part that changes is what comes before rasterization. So let's get rid of this. So I have some data of different types. My custom data, and my mesh shader is going to have access to it, and it's going to output some primitives to rasterizer. Now I draw it this way intentionally. Instead of putting my data over here, I'm putting it down here, because this is a little different. On the same line, you know, like we're pushing vertices, we say GL drove vertices, and you send all these vertices, they just pass through your, all of these vertex attributes pass through your rendering pipeline over here, right? It's not the same. So like if our general graphics, regular graphics pipeline is like this, I have my vertices, vertex data, and they pass through here. Of course, the data changes as the data flows from one end to the other, but it's this data, you start with data and you start passing this data through this pipeline. Over here, things are different. In a mesh shader, I'm not pushing anything to my mesh shader. I'm not pushing anything to my mesh shader. My mesh shader, if it wants, it will request data. Just like reading a texture. In your GLSL code, you say, oh, give me this texture value at this particular coordinate, and you get it. In a vertex shader, that's not how it works, right? So the vertex attributes appear inside your vertex shader because they're pushed over here, right? So I'm not doing the same thing here. The programming model is a little bit different. You pull the data. You just access the data that you want, right? Now, yeah, so this was our typical graphics rendering pipeline, and we're replacing it with this stuff. So rasterizer, rasterizer. So you see something missing here? I mean, we're familiar with this, all of this stuff, right? And over here, this seems a little too simple, doesn't it? Oh yes, it is simple, and that's nice. Well, I've been talking about how nice that it's simple. Everything is combined together, and I have a computer that can do anything. There's one important missing element here. So in the regular graphics pipeline, what happens is I start with vertices, and then I come to the tessellator. Over here, all of a sudden, there's this huge explosion of data that happens. I come here, beyond this point, I'm going to have a lot more data if I'm using tessellation. Here, all this explosion needs to start from the beginning. I mean, okay, I can do that. I can generate however many data that I'm like. It's okay. I can generate however many vertices I want in a mesh shader. That's okay. But in terms of parallelism, I'm losing some stuff. So I had some parallelism in the order of vertices that I'm sending to my graphics pipeline. And after here, I have a lot more vertices. All of a sudden, I have a different level of parallelism, right? So I started with some parallelism, and then I have a lot more vertices to operate on in parallel. And Geometry Shader sort of messes things up quite a bit. This is a too powerful shader. It just consumes whatever, outputs whatever. It sort of messes up this whole parallelism quite a bit. But so ignoring the geometry shader, what's happening here is that I have some parallelism. I have a lot more parallelism later on. Now, if I'm going to operate on whatever I'm going to output in my mesh shader, the parallelism that I want here is going to be this level of parallelism, right? Because that's going to be my output. I want to have this level of parallelism in my mesh shader, but I'm not quite going to get it, right? I mean, I can, but in that case, I'm sort of probably wasting a lot of things that I could compute more efficiently here. So I really want to have this model of start with low resolution stuff and then operate on higher resolution stuff after I generate some data. For that, mesh shaders allow this expansion using task shaders. So our initially mesh shaders will initially I'm going to use some task shaders instead of dispatching mesh shaders directly. I'm going to be dispatching these task shaders, and then inside these task shaders in each group, I will decide whether or not I want to dispatch mesh shaders. So these are like larger coalesce groups of things, and from that I decide how many mesh shaders that I would like to run. And there's going to be this mesh generation stuff. This is not actually generating anything. It's just basically I am calling more, I am deciding to run a lot more mesh shaders. So this is going to run in the parallelism level of this stuff, like where I have a lot more data and a lot more parallelism. And this is going to run at a relatively higher, lower resolution level of the level that I will be using over here. Right? So this allows me to sort of replicate the same behavior that I would get with the traditional graphics pipeline, but using this completely flexible compute shader-like shaders using task shader and mesh shaders. So if this task shader name does not mean much to you, DirectX actually calls it something else. It calls it amplification shader. So its job is to basically generate more and more data. I'm honestly not sure if that makes more sense, but whatever. It's that's what they're called. All right, so let's see how you can use mesh shaders. For mesh shaders, these are going to be draw calls because this is actually graphics rendering stuff, right? But it's a special kind of draw call, draw mesh task, NV. This is an NVIDIA extension. It's not a core part of OpenGL at the moment. It's not in any OpenGL core version, but it is provided as an NVIDIA extension. So if your GPU supports this particular extension, you can use this. And this is supported by AMD hardware as well, the latest AMD graphics cards as well. But the extension is an NVIDIA extension, and the code looks very much like a compute shader actually. Of course, I'm saying, okay, I need this extension. Yeah, this is the OpenGL version, but I also need this extension. And then this is it's the same thing that we had in the compute shader. This is really bad. I said 1, 1, 1. Basically saying I just need one thread. I have probably 32 in a warp, so the other 31 will be just sitting. Probably not great. So not good at all. Don't do this. But it's a simple mesh shader example. So I also need to specify, this is a special kind of compute shader, so I need to specify its output. So I'm outputting something. I'm outputting, let's say, 1 primitive and 3 vertices. These are the maximum numbers. I can decide to output less. And the shader code is could be something simple like this. So I have these vertices. I'm outputting these 3 vertices. Vertex positions are here. And I'm forming a triangle here. That's my primitive. And I outputted this primitive. I'm done. So this is a pretty bad mesh shader, but it's a very simple mesh shader example. So the way that mesh shaders are recommended to be used today. Now these are super flexible shaders. You can do whatever with them, right? So, but the way that they're recommended to be used is using this concept of meshlets. So you would take your mesh and pre-process it way before rendering while you're preparing your asset, and you split it into multiple meshlets. These little pieces here, and then each one of your mesh shaders would operate on one of these meshlets, and so you can do things that you couldn't do with the regular graphics pipeline. For example, you can do very early culling. For example, if a particular meshlet you decide that it's occluded by something, you don't have to draw it at all. You can just throw it away. So if you use mesh shaders for replicating exactly what the traditional graphics pipeline is doing, you might be able to squeeze a bit more performance out of it, maybe if you write your mesh shaders just right, but the traditional graphics pipeline is fairly well optimized too. It's really hard to beat it. You can maybe, but if you make any mistakes, you're going to be even slower, so it's probably not the best use case of mesh shaders. But you can think of mesh shaders as an opportunity to do things that you couldn't do with the regular graphics pipeline, with the traditional graphics pipeline. So that's where they start shining. That's where they become really, really powerful. So this whole concept of meshlets, for example, is something that we couldn't do with the traditional graphics pipeline. And that's where they're very, very powerful. So this model, I took it from this wonderful talk. There's the link to it in the course website. So I highly recommend that you just go and watch it if you're interested in mesh shaders. It's an excellent talk based on DirectX, but it's the same idea. So I would highly recommend it. Check it out. But I want to end this lecture by showing an example of mesh shaders with this NVIDIA demo. It's a pretty impressive example. Here there are quite a lot of triangles. There's so many more triangles than our GPU can possibly draw. But the only reason why this runs at real time is that because we're not actually drawing all of these triangles. This is using level of detail. We talked about level of detail. So not all of these meshes are drawn with the same resolution. So look at this. Look at these numbers. They're crazy. So what is this? How many triangles I have in the scene? 1,000, million, billion, trillion. 3.5 trillion triangles I have. There's no way you can draw this in real time. Not possible. But 50 million? Yeah, we can do that. We can do 50 million. So what it's doing is that on the fly, using mesh shaders, it's deciding which triangles to draw, which meshlets to draw, which objects to draw, and which resolution. And this is how we can get this performance, and this kind of a scene can run in real time. So these are different levels, very much like tessellation, but this is drawing mesh shaders. It's not using tessellation shaders at all, but I have different tessellation versions of these asteroids, and it's rendering them at different resolution based on where they are on the screen. So you basically can't really tell the difference, and this way we are able to render a massive, absolutely massive scene. Actually, this scene is generated with instancing. We don't even have all of these separate asteroid models. We can't even store a model with 3.5 trillion triangles, was it? Vertices? Whatever. It's too many. There's no way even to store it, let alone render it. Like, it's not going to happen. But with mesh shaders, you can do things like level of detail at a level that we couldn't do before, and that's how we get this performance, and we can render them. All right. So this was our topic for today. I wanted to cover compute shaders and mesh shaders. So this way, I believe we covered all of the shaders that we have access to on the GPU. And you guys, I believe, have started or about to start working on your final projects. So hopefully this discussion will be helpful to you. Now, I'm going to tell you something. If you're going to work on a method that was invented before we had compute shaders or before we had mesh shaders, you might want to consider whether you would like to use these newer hardware features in your current implementations. So whoever came up with those ideas that you're re-implementing, maybe they didn't have access to these new features, and that's why they had to do things a little bit differently. There might be better ways of doing the same things today. So keep an eye on those. And that's why I wanted to talk about these shaders earlier. So before we start talking about more advanced graphics topics. So this was this is all I had in mind about compute shaders and mesh shaders. So that's the plan. I'm going to start talking about more advanced graphics stuff going forward. Yes, okay. I'll end it right here then. Thank you all for joining, and I'll see you all next time. All right.